Thank you very much. So let me put this. So welcome everyone to, let me remove this because I don't see it, to my presentation about the frequency dependent AC resistant modeling of magnetic component using ladder network. It should have been shorter. Anyway, you'll see. So as you have seen already, normally engineers go crazy with some models, especially with some components, especially semiconductors, but not to others. The others, so I feel like, okay, we have to improve this a bit. And already last year, we presented a basic circuit for magnetic components in Simba. And we included the DC resistance and the primary leakage inductance and the core reluctance on that. But come on, this is not enough. Because as we know, magnetics are complex. We have a skin effect, we have proximity effect, and when you put all that together, the resistance curves that we get, the famous Dole's curves, they tend to be basically the opposite of linear at the end of the day. So how to simulate that or how to deal with that? There have been some other softwares that, especially the one from Ray Ridley, that they popularize the ladder networks in the last decade. And what they do is, they get this curve and they try to model the behavior of these non-linear components with a ladder network, which is just a number of inductances and resistors put in a ladder way. So with the frequency changes, the resistance that the rest of the circuit sees from the modeling, from the magnetic changes with that frequency, and it tries to model the real one that we measure. You can also do it for the core losses, and that's probably for the future. But the thing is, as I said, Ray Ridley had this in his software, but this is not something that recent. This was actually an old concept from the 50s, invented by T.G. Lewis, or this is the first actually paper I found that they talk about this. And the idea is to always try to model things that are not electrical with electrical components. But for this kind of model, typically you need measurements. The first step is always to build the model, the magnetic, then you need to measure it, and then you can create the model for whatever software you are using, all software you are using, not this one. This was much better. But I cannot do that because I have a software for designing magnetics. So when my users are on using my software, they are designing the magnetic. They don't have the component. So what I do is I allow them to design the magnetic, simulate, and then I have a lot of analytical models, and I do a frequency sweep with all these analytical models, and I get something similar to the measurements, but from the models. And with that, we create a model for Simba. How? Well, at the end, this is just simple, or like not math, but programming. Like you can do there's a bunch of libraries that you can use. Typically, all of them use the Levenberg-Marquardt algorithm. For Python, you can use SciPy, like curve-fit, so functions curve-fit from SciPy. For C++ or C, you can use SciPy leftmark. Then you have also more similar or more famous ones that they use in C that use Fortran, but this is pure C, which is also nice, especially if you need to compile for the web browser where Fortran is not welcome. So at the end, what we do is we model this, we calculate the ladder that the frequency sweep that we need to adjust. We apply some algorithm, and we do some Simba code to create these models around. We put the resistance. We use we create a JSON that Simba can read, and basically we create one model that is able to behave in the same way as a real magnetic, like AC resistance change over frequency on Simba. And until this point, I have a demo. I have like some slides of what to do, but in reality, I mean, we have software, so the best thing in general is to do a demo. Let me see. Let me know if you can see. You can see open magnetics all fine.
Yes.
All good. And if you have any question until this point before the demo, it's also fine. But I will be fast. Don't worry. If not, and normally what we do is we create a new magnetic design, and this is loading the engine and the database, because And then in the first step, we have to define the requirements. I'm going to use typically because I close. So I'm going to have just one that is the flyback that Simba that comes with Simba as a template, so nothing fancy, right? So I'm going to I simulated this. I exported the waveforms, and then what I'm going to do is load everything here. So this is 220 micro, of course, one output, a turn ratio of 3, and because we want to be cool and fancy, we are going to use planar transformers, not GUNT. We click on continue, and here we select that we want to use an export file from Simba, which is this waveform CSV that I just simulated before. We need to put the frequency, 100 kilohertz, and we confirm that these are the columns. If this, and the same for the second, and this is not correct, we can select which columns we want, but normally it graphs them automatically. And then we build our magnetic. We can, I'm not going to do a demo of open magnetic, we'll go fast, but you can get an advice core and you can get all the cores that you want here. Similar for the winding. For the planar, we can see how it proposes like 5 layers, 1, 1, 2, like primary, primary, secondary, primary, secondary. And the nice thing that I just added, and this is the nice thing for you guys, is that there's a button here now for Simba. You can download more stuff, but for Simba, you have two options. One is to directly download the library, or the first one is to attach a file. Attach a file means that you already have a simulation, and it's read, processed, the model is created, and now you get to download another file, another Simba file with the library already included. So if we open this one and we look in libraries, now there should be here one section for open magnetic components and one magnetic that we just created. And if we get into it, what we have here is the same as we had before, like the reluctance circuit, the windings, but now we have some AC resistance model as a ladder network, all 5 levels. You can configure the levels as to make it faster or slower and more accurate or not. But again, like this is like the standard one. And then what you can do, just go here and again simulate it. And then we can also simulate the ideal one just to have the comparison. And if we look at the output current from the ideal one and the real one, and the one with the parasitics, like with the AC resistance, we can see, so this is green one is the ideal one, and we can see the oscillation, typically when you start with a flyback and all that, and the startup. But here we can see how it is dampened already quite a bit by the AC resistance that comes from the transformer. This is what will happen in reality, because you have a bit of resistance that will go over frequency. And yeah, and this is something that is one of the first steps. Now, it's really nice that you introduce nonlinear magnetic circuits, so we can add more like core losses and saturation and everything that will create really nice models. But this is at least for now. And that's it. I promise I was going to be fast. I don't know if you have any questions. If you, all this can be done for planar, also for GUNT transformers. You can import all kind of CSVs directly, or even measurements if you want. And that's it. All this is also here in the slides, so don't worry, you will have this available too.
So thanks a lot, Alfonso. So if anybody have questions, you can type them in Zoom. I do have a question. That's super cool. First question is it possible in open magnetics to actually see the frequency dependent impedance of the magnetics?
Ooh, I love that you say that question. You can go to settings, you can enable graphs, and it depends on the material. Sometimes the material has the impedance curve, like for example, not this one. So let's see some that has it. Hopefully Ferrous Cubes has it. Nope. Normally you can, but if I don't know, maybe I can change we can try another material now.
Oh,
But
sorry,
what you
but
can
that I
see
should not
here,
have asked the question.
no worry. What you can see is, for example, the resistance over frequency. This is for a planar, and then you can increase the frequency to have it larger, because again, like planar transformers are like especially good for this. Let me actually try. I know that micrometal should have it. Let's put something like this. Yep. So hopefully this, nope, doesn't. No, my bad. Because no. Yes, it does, but not for planars yet. So that is my bad. So let me actually quickly do the same for wounded. So literally just 30 seconds. And then this is something I should know by heart, don't do.
Uh-huh.
So yes, we can see it now with this
And
proposed
and
material.
and can we see the result of the fitting that is actually exported to Simba, or will we
No,
have to use Simba for that?
exactly. This you can see exactly. So you can see the fitting I used, the data I used to fit for Simba, which is the resistance per winding over frequency. You can
Okay,
select the primary or the secondary.
that's the input. And if we want to compare, yeah, because I played a few months ago with something very similar for a client, and it was not easy to actually, in our case, to have a good curve fitting. But it's possible in Simba to have an AC sweep just on the impedance and extract the
Yep.
impedance over the frequency, and then we can compare. Cool.
Yeah,
Thank you
we
so
could do.
much.
It could be done actually to have like once the code I have is in C++. It's open source. We can integrate it and then create a Simba, the sweep from a measurement from Simba instead of from analytical models. That should be simple. I
Or
mean,
even
the library is not simple, but it's already done. So the library is already integrated and working for WebAssembly. That I know that you like it.
yeah, but actually, to get the curve fit, we don't need even Simba. We can we can calculate it analytically
Yep.
because
Yep.
just like RL components that adds up.
So
Okay.
what would be cool is to just do this analytically, do the fitting, and then run the sweep in Simba, and then see the result.
Oh yeah, that would be nice.
But for next year.
Awesome. Yes. Awesome. Thank you so much, Alfonso, for your great presentation. And yeah, looking forward for another advancement in the open magnetic Simba support next year.